Morning, everyone. So this lecture is a short lecture on the EM force and how it relates to atoms and molecules. So the EM force is attractive between electrons and protons. Electrons are attracted to protons, protons are attracted to electrons. But electrons repel each other, protons repel each other. So that's because negatively charged particles repel other negatively charged particles but attract positively charged particles. And positively charged particles repel each other. So this is the force that holds electrons to the nuclei of atoms. It's also what makes electrons be attracted to the protons of neighboring atoms that causes atoms to bond together into molecules, making these vastly complicated molecular structures like us. And it's also what drives chemical reactions. Chemical reactions are when molecules change form into other molecules. So there's many chemical reactions happening in your body, for example, that cause us to be living beings. So here's a hydrogen atom, a depiction of a hydrogen atom. The proton at the center, that's the nucleus. A hydrogen atom has just a proton for a nucleus. And then it's surrounded by the electron, because the electron is being attracted to the proton. So this has a negatively charged particle and a positively charged particle. So the net electric charge of this atom is 0. If you add +1 to -1, you get 0, right? So neutral atoms, normal atoms, have the same number of protons and electrons. So for instance, a carbon atom has 6 protons in its nucleus and then 6 electrons surrounding the nucleus. 6 + 6 - 6 is, again, 0. So a neutral atom always has 0 net electric charge. So here's a bunch of hydrogen atoms in close proximity to each other. Each one has 0 net electric charge, so they don't attract or repel each other, right? The atoms don't attract or repel each other because each one has 0 net electric charge. So they don't attract each other any more than the neutrons attract each other because they don't have any electric charge. So you can think of it this way. Every the electron on, say, the upper hydrogen atom is being attracted to the proton on the lower hydrogen atom, but it's also being repelled by the electron on the lower hydrogen atom. So there's no net force. It's sort of being forced in 2 different directions at the same time. But if, here's a depiction of 2 hydrogen atoms in such close proximity that the electrons actually cross each other. The particles that make up atoms, electrons, protons, neutrons, are not like hard pool balls where they get close to each other and they bounce off each other. It's different in the microscopic world. They can actually be in the same place at the same time in certain cases. And so you can see here that part of the right electron is closer to the left nucleus than part of the left electron is. Right? So this part is not being repelled from that atom by that part of the other electron. Does that make sense? And in fact, it's being sort of forced toward it by that repulsion. In other words, now the forces are not perfectly balanced, and that causes this attractive force. And this is a crude depiction of 2 bonded hydrogen atoms. Hydrogen, under normal circumstances, hydrogen gas, is in this molecular form, 2 atoms bound together into molecules, and that's what normal hydrogen gas is like. Now you might wonder, can a third hydrogen atom come in here and do the same thing? Well, in this case it's limited to 2 for reasons that we'll see later on. But these 2 electrons now occupy the same space in a different kind of shape. They're not spherical anymore. They've now taken on a different shape in this hydrogen molecule. So this is, it's this attractive and repulsiveness and the ability to cross over and be in sort of the same place at the same time that is responsible for certain kinds of atomic bonds. This is called a covalent bond, as we'll see later. So I'm going to talk a little bit about the multiple interactions between particles. Part of the exercise that you'll do has to do with particles being repelled and attracted by multiple other particles. So here's a positively charged particle and a negatively charged particle. I'll make them the same size here, even though electrons are a lot bigger than the protons, but just for simplicity's sake I'm showing them the same size. So these, of course, attract each other. So there's an arrow on each one indicating that the particle that the arrow is on is being forced in some direction. In this case, it's being forced toward the other particle because it's an attractive force. Here is two positively charged particles, and of course they repel each other. So I've got one arrow on each one. But what do you do if you have something like this? Here's two positively charged particles and a negatively charged particle. Well, each of these particles has two forces on it, right? So the topmost positively charged particle is being attracted toward the electron. That's that one arrow pointing toward the electron, or the negatively charged particle. And it's also being repelled by the other positively charged particle, so that the other arrow on there indicates that. So each particle has two arrows on it, and indicating that they're being forced by two particles at the same time. Now, if someone had a rope around your waist and was pulling you forward, and then another person had a rope around your waist and pulling you to the right, now you have two forces on you. Which way are you actually going to go? Well, you're going to go in a direction someplace in between, because the total force is in between, and that is represented by this diagram. So the blue arrows represent the total force on these particles. So for instance, the blue arrow on the negatively charged particle is in between the two forces on it, and it's actually a longer arrow because those two forces are pulling kind of in the same direction, and so they're more adding up to each other, and so there's a relatively strong force on the negatively charged particle in that direction. Whereas the topmost positively charged particle, it's being pulled in two directions that are kind of almost opposite of each other, and so the force is not as much, but it is being pulled in a direction that's sort of between those two forces. So if there was two forces on a particle that are exactly in the opposite direction, but the same force, then there wouldn't be a blue arrow on it at all, because the net force, the total force on that particle, would be zero. So this part of the exercise is just to illustrate that one of these charged particles can have multiple forces on it at the same time. So you can think of it that way when you have the hydrogen atoms in close proximity to each other. So each of these electrons is being attracted to each of the protons, right? But also being repelled by each of the other electrons. So so there's multiple forces going on here, and that's how you can begin to understand. And here again is this picture of this lithium atom where there's three protons in the nucleus. Again, I'm not depicting the neutrons in the nucleus, but just for simplicity's sake. But they're surrounded by three electrons. So now an additional electron is going to be out there. It won't feel a net force toward this because it's being attracted by three protons but repelled by three electrons, so there'll be no net force on it, right? And the way the electrons stack up, we'll see why this is later, but there's two electrons in this inner part, this inner shell, as it's called, and then the next one is on top of that. So that next electron up, the third electron of this lithium atom, it's being attracted by all three protons, but it's being repelled by the two inner electrons, right? That means that it's being attracted by three particles, repelled by two particles. So the force attracting it toward the nucleus is the same as though it's being attracted by one particle, right? Because 3 minus 2 is 1. So the attractive force on that third electron is weaker than on the other two electrons because it's being repelled by those two inner electrons. Now, the significance of that is the outer electrons of atoms are being held on to the atom more weakly than the inner electrons, and that is important for understanding the way bonds work, as we'll see later on. Okay, so this should get you started on the exercise.